Right then, so turning points, as you probably noticed in the specification, looks at the particle nature of matter, the electron stuff we've been looking at. It also looks at the wave nature of stuff. And one of the first things that people started to argue about whether it existed as a wave, of course, was light. And the video we watched last time gives you a bit of a summary of the key ideas. First of all then, let's make a very brief summary of ideas of light. In ancient times, so the ancient Greeks, people like that, you had particularly, I'm sure many of them had ideas about light, but we saw a bit, if you remember, about Empedocles, the guy who jumped into the volcano. He came up with it, as I say, it sounds mad nowadays, but actually, probably at the time didn't seem too outlandish. The idea that vision and light is something you do to something, all right? You say, right, I'm going to have a look at this whiteboard. You turn your head and you do it, and you're not looking at that thing over there, you're looking at this thing over here. So he was very keen on the idea, a bit like a lighthouse, that your vision is sort of a beam that sweeps around wherever you're looking, and that the light is effectively coming out of you, going to the thing. Okay, as I say, nowadays that sounds bonkers, but at the time, it's probably not too unreasonable, fairly close to people's perception of vision, and therefore it was quite a popular idea, and developed on by people like Euclid, who were very into things like straight lines and curves and all sorts of stuff. He spotted the idea about, basically discovered the idea of angle, didn't he? I think on the video it talked about a distant column, which is actually very high, and your thumb, for example. So if you hold up your thumb and something like a door over there, they appear to have the same size because they are effectively the same angle, okay? And this is all to do with the idea of straight lines, okay? A very important figure, around about 1000 AD, Al-Hazen, there's various ways of spelling it. Obviously it's written originally in Arabic, so it doesn't go into the 26 letters of our alphabet very easily, but that's one way of writing it, Al-Hazen. And he, apparently, was one of the first people to make the absolutely fundamental discovery that in fact it's the light going the other way. Something like the sun, for example, and something that you're looking at, the light essentially bounces off like that, and light is coming from a source of light, hitting objects, reflecting off them, not just mirrors. Light doesn't reflect just off mirrors, it reflects off everything, and some things, obviously like the table in front of you, is reflecting light, and that's how you can see it. It's not reflecting as much light as a mirror, that's why it's not as bright, but very importantly, he got the arrows turned round. Okay? A lot of Euclid stuff works fine, even though he thinks the rays are going the other way, because of course often ray diagrams you could have the light going in either direction. But an absolutely fundamental discovery, which is why he didn't get enough credit, I don't think, in a lot of textbooks. Really important discovery, the idea that light reflects off things into our eye. He also found out about the angle of incidence equal the angle of reflection and stuff like that. Stuff that's often credited to people who come much later. Okay? And as it said on the video, he famously had wrote a 7-volume theory of optics and light and so on. And we know for a fact Isaac Newton had a copy of this. He had a translation of this in his library. Although he never acknowledges the work of Al-Hazen, I'm sure the great optics by Isaac Newton owes much to this. Okay? And that brings us on to, I would say really, coming a bit closer to the syllabus, mechanical theories of light. Theories of light as a physical thing were quite popular at that time. Apart from just describing how light behaves, we're now moving into trying to explain why it does what it does, or what it actually is. Okay? And there were two people really who developed mechanical theories of light. First of these we'll mention is René Descartes, the French philosopher, mathematician, scientist, etc. And of course, Sir Isaac Newton. Okay? Both had theories which had light basically as a little stream of particles. Okay? In Descartes, I think they were spinning, and in Newton's they were sort of vibrating as they went along. But they were both what you might call mechanical theories of light. That light is actually a thing. As you know from the video, Descartes was very into the idea that most things are just a system of levers and pulleys and things working a bit like machines. And he tried to apply this idea to light. Okay? He famously produced the formula for refraction, sine I over sine R equals n. I've lost track of the number of people who famously did this first. There are many, many people, even Al-Hazen, you know. This is an equation that has so many fathers. There's a number of people. It's called Snell's law in your textbook, but many people came upon this idea. And we have to mention, partly because it's an absolutely fundamental piece of physics we're going to walk straight past, in developing this, the French mathematician Fermat, who came up with his principle of least time. And it's a really, really powerful way of analysing how light behaves, is you say, well, this medium is quite easy to go through, and this one's a bit harder, so what path could the light take that it would cover in the shortest time? And you can actually use that to work out, I'll show you another time, you can use that to work out why sine I over sine r equals n. Okay? So Fermat's principle of least time is a really, really important principle in optics. We're going to just got to slide past it there. But he would have a definite claim to really justifying, explaining why this formula happens. And that's what I like about it. It's not just saying I've discovered this happens, it's saying here's a reason why. Light takes this path and not others because it's the path of least time. Okay? Now, the two theories, how would you tell between them? It's a bit like the ancient Greeks arguing about atoms. How are the ancient Greeks ever going to tell if the world's made of atoms or not? Because they haven't got the technology to do the experiment that would decide what they called on the video a crucial experiment, an experiment that would either prove this theory right or that theory right, but basically after this experiment, neither, at least one of the theories is not going to be accepted. Okay? A number of things don't really help. Reflection, they can both explain reflection quite well, and refraction works quite well also. Interesting though, Newton's theory of refraction had things speeding up as they go into glass. He could explain the path it took, but it required him to have the light going faster in glass than it did in air, which didn't seem to matter at the time. This is one of the things actually mentioned in your syllabus. This didn't seem to matter at the time for a number of reasons. One, Newton was so famous by then, and also, how would you know, really? As long as you can predict the right angles, if your theory has the light going faster in the glass but gets the right answers in terms of which angles it predicts, who would know? So again, these are not crucial experiments because they accommodate both theories, all right? Newton, I think, the video was quite clear about this. Newton, I'm sure, read the front cover and immediately he realised it was written by Descartes, who was French and Catholic. Newton was immediately out to find a way to prove him wrong. Reflection and refraction was never going to do any good to him, and he realised immediately that what Descartes had about colour was the thing that was going to make, that would allow him to prove him wrong. Okay? And this leads us to, if you think of the sort of big contest between the theories of Descartes, theories of Newton, then you have Newton's first crucial experiment, as it was known. And if you look at the experiment, it's clearly designed to prove Descartes wrong. It's not sitting down saying, let's investigate light. It's an experiment designed to prove Descartes' theory wrong. Descartes, as you know, had white as the pure colour. So white as the driven snow, etc., etc. White is the pure colour. And as it goes through a prism, it gets changed in some way, in a number of ways, to make it red or to make it blue. Okay? Newton suggested that was completely wrong. And he developed his experiment whereby you send light into the prism, you send white light or sunlight to the prism, you split it up into the various colours, red, orange, yellow, green, blue, etc. And then what you do is you just use a little bit of red light, and of course think how much light you've wasted now, so unless you've got a very, very bright day, this is going to be quite difficult to do, hence Newton shutting himself in darkened rooms all the time, and particularly the British level of sunlight, it's going to be quite a difficult thing to do. And he then said, well, let's send that red light through a second prism. And if Descartes is right, then something other than red will come out. If what prisms do is they take light and they change it in some way, they take the pure white light and they spin it faster or slower, I think Descartes had, then whatever would come out of this wouldn't be red. It might go back to white, we don't know, but the point is it wouldn't be red. And if you do this experiment, of course, you do just get red light out of it. And Newton has shown here, of course, that red, orange, all the way down to blue, these are the Lego bricks, these are the building blocks of light, and using all the colours of the rainbow, all the colours of the spectrum, you can build up white light, which, as the actor on the video said, it's white light that is the mixture. Not white light that's pure, white light is the mixture. It's made up of the pure, independent colours. Okay? In a sense, this is a very important experiment because it shows Descartes' theory is wrong. It doesn't explain much more, to be honest. Newton had this idea that red light is particles vibrating slowly, and blue light is particles vibrating very quickly, which is quite close to the wave theory, isn't it? Because in the wave theory, blue light has a higher frequency, doesn't it? And red light has a lower one. But, I mean, guessing's a bit strong. They didn't have any technology really to investigate these things. Both men were conjecturing to a large extent. But this is the first crucial experiment that shows the difference between the two. Okay? Now, moving further into your syllabus, it wants you to have a look at the distinction between Newton's theory of light and that of people like Christian Huygens. Okay? So that's the final thing we'll just do in this bit. So Newton has this theory of light. It works very well. It explains reflection, it explains refraction. Very spectacularly, it explains colour, which Descartes' theory doesn't, or explains it correctly. Okay? We now have Newton and his corpuscular theory, which is a particle theory, and set against that is the theory of people like Christian Huygens, Huygens, a Dutch astronomer and scientist, mathematician. And he suggested light was a wave, okay? It was a kind of wave motion, a ripple through space, which we now know to be much closer to the truth. But again, what we need to do as scientists, well, in that case, we need to decide what would be, in this case, the crucial experiment, okay? The crucial experiment for colour between these two mechanical theories was this one that Newton designed. But what experiments could you do that would solve this problem? Well, the first one that wouldn't work, of course, would be reflection. Light bouncing off at I equal to R works fine on the corpuscular theory. So this is what Newton termed his theory. His mechanical theory was called corpuscular because light was made of little tiny corpuscles or blobs. Okay? Even refraction, even though Newton had to assume that the light speeded up into the glass, he still got the right answers. And nobody could measure the speed of the glass, so nobody would know. So these two are no good because both theories work fine with reflection and refraction. The important ones here are things like diffraction, interference, and polarization. Okay? These are the important ones because you can't do these things to corpuscles. You can only, for example, interference is a good example, you can only get two light waves cancelling each other out to give darkness. You can't do that with particles, okay? So these are the crucial experiments, but again, history's a bit the wrong way around. Newton died in 1727, okay? Huygens, I think, was a bit younger, but the point is, and your syllabus actually mentions this, which is interesting in the turning point specification, it talks about why Huygens' theory, which is clearly right. And actually, if you think about that sentence, that's nonsense. It's not clearly right, is it? In the 1700s, what's clearly right about it? Again, we are still hypothesising, we are still conjecturing. Descartes and Newton's conjecture. Newton's managed to do an experiment to prove that he is correct. But neither of them has particularly got absolute reasons for any of these. They've got experiments, they've got things they observe which suggest to them that it's corpuscles or suggest to them that it's waves. We still don't have the knockout punch. We don't have that crucial experiment. But things like interference, coming back to your specification, first experiment to do interference of light, which you should remember from year 12 was Young's double slits. Do you remember that? Tricky to do. I mean, the exact date, even when Young did it, was a difficult experiment because to get light to interfere with itself, you need two sources which are coherent, all right? Whatever their phase relationship, they need to stay either in phase or out of phase or something like that. Whatever their phase relationship, it needs to stay constant, and that's not easy to arrange. But there's a long gap between the time of Huygens and Newton's to Thomas Young doing this experiment, and that's why, I guess, as I say, your specification says reasons why Huygens' theory was not immediately accepted. Basically, it was their relative status at the time. Newton was the Stephen Hawking of his time. You know, there was no greater physicist than Isaac Newton. And Huygens' suggestion, very few, unless there was some really concrete evidence, very few scientists were going to line up behind Christian Huygens. against Sir Isaac Newton, even though Newton didn't really have much more evidence for his theory than Huygens had for his. It was kind of Newton was, in position first. And the second reason is the crucial experiment. If these theories are different, what experiment can you do that would prove one of them wrong? And it's things like interference, which of course technologically were not possible until a great deal later. Okay? So to answer the question in your specification, this is why the wave theory was very slow to be accepted, and for many years after Newton's death, people were still taught the corpuscular theory in school, even though it's not actually the right one. It was Newton's status and the lack of this experiment. I think, should they ask you a question like that, some sort of philosophy type question, give reasons why Huygens theory was slow to be accepted. It was Newton's status and the lack of this experiment. If this experiment happened in their lifetimes, it would have been very different. If Huygens had been president of the Royal Society or something and had the theory of gravitation and laws of motion behind him, again, things would have been different. Okay?